All right, making a couple of quick videos here. It's looking like a lot of the ones you have questions on were problems where you have the same index. So like these are both square roots, but they've got different radicands. The numbers underneath are different. Um, One way we can fix that is to check and see if either of those radicals can be simplified. And in this case, both of them can. Because we're talking about square roots, we want to find perfect squares that evenly divide into both of those numbers. Perfect squares, numbers like 4, 9, 16, 25, 36, so on and so forth. You can just Google perfect square to get a list of those numbers. So for 72, the biggest perfect square is a 36, and 36 times 2 gets you to 72. The reason, again, I picked 36, it's a perfect square, and it also divides evenly into that 72 that we wanted. 18 is the same as 9 times 2, and again, 9 is a perfect square, so that's why we picked 9. So doing a bit of simplifying here, there's still this 9 out front that's coming down. The square root of 36 is 6, and this 2 is left behind. It's still under a radical. The square root of 2 is just root 2. Plus, we have a square root of 9, which is 3, and likewise root 2 coming down. This addition problem becomes easier to see now. We have 2 root 2's. Purple was a bad choice. We have 2 of those root 2's hanging out. So now we know we can add these 2 radicals together. A bit of cleanup, 9 times 6 is 54. So we have a 54 root 2 plus a 3 root 2. So I'm adding 54 and 3 to get 57. 57 what's? Root 2. The second one you sent me, very similar. All 3 of these are square roots. There's 3 of them, but the process is still the same. We can break all of these down using a perfect square factor. With 20, we can do 4 and 5. In this case, 4. 4 is a perfect square. 125, 25, and 5. And then root 5, we don't have a perfect square factor for root 5, but that's okay because these are all going to be like radicals. They will all have a root 5 in them by the time we're done. So the square root of 4 is 2, so I have a 2 root 5. The square root of 25 is 5, so I have 5 root 5. And then we also have this negative root 5 at the end. So I've got 2 apples, and you give me 5 more apples. That's 7 apples, but then we eat 1, so there's only 6 left. 6 root 5. The 3 that you sent me, very similar. You can break that 72 up into 9 and, 9 also works, actually. It's probably worth mentioning. You could break that one up into 9 and 8, but then notice 8 would be broken up into 4 and 2, so there's a bit extra work going on there. It's helpful to find the biggest perfect square factor when you're trying to break down a radical. So 36 is bigger than 9, so I would recommend going with 36. So 3 is going to be very similar to the previous 2. The fourth one you sent me is super different. Because notice these are no longer square roots, they are now cube roots. So these indexes match, they both have a 3. But the radicands are different. Unfortunately, we're not looking for perfect squares anymore. Now we're looking for perfect cubes. So not just number times itself, but a number times itself 3 times. So 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. The next one will be 64, followed by 125. So these are our perfect cubes. Again, just like with the squares, you can Google a list of perfect cubes and get them fairly quick. Extend too far. So these are now the numbers we want to break these radicals up with. 40 we can break up as 8 and 5. Again, the reason why I'm picking 8 is because 8's a perfect cube. So if you tried to break it up into something like 4 and 10, for example, 4 is a perfect square, but it's not a perfect cube, so it doesn't help us with this problem. 320, I believe, splits over 64. It does. So that's a 64 and a 5. Again, you'll notice we've got those matching radicals. The radicands match, the indexes match. So we will be able to add these together after doing a bit of cleanup here. Still have a 5, don't want to lose the 5. The cube root of 8 is 2. That's a number times itself 3 times, it gets you 8. So that's what we found over here on the right. So the cube root of 8 is 2, and then a cube root of 5 is tagging along. Let's see, we also have the cube root of 64. I didn't write the work for that one, but the cube root of 64 is 4, because 4 times 4 times 4 is 64. And we got a cube root of 5. So cleaning this up, 5 times 2 is 10. That's coming from these coefficients. So we have 10 of these ugly cube roots. We're adding 4 more of these ugly cube roots. So put that together, we have 14 cube roots of 5. And this video is long enough, so we'll stop here. This is the addition and subtraction ones you wanted to look at. And I'll make a separate one for the distributed property.